To the next video in the systems programming video series. In this video, we will be moving on to section 4.3, discussing signed binary integers, and so in the textbook Dive into Systems. The question here is, what would you do if it were your job to take sequences of zeros and ones, and they maybe start at all zeros and they maybe go to all ones, but somehow with a system like this, your job is to represent at least some negative numbers. How would you do it? Well, after a certain amount of thought, maybe you even want to pause the video and literally try to do it yourself if you've never thought about this. But after you have unpaused the video, a natural first guess is to simply reserve one of the bits, probably the very final bit on the left, although it doesn't really matter, but reserve some bit as your sign bit, right? So basically, the way that sort of one's complement works is that the last collection of bits, everything other than the first bit, is read in exactly the same system as an unsigned integer, as we've already discussed in the previous video. But this final bit acts as a sign. And by convention, we tend to take 0 to indicate no sign, which by default we take to mean a positive number or a non-negative number, I guess. And then a 1, right, a 1 bit in the leftmost position is interpreted as having a sign, which we take to mean negative. Now, if we do this, there is, it's a nice system in that it very much reuses everything that we already know, in the sense that, so if I want to count, I know that, this is my number 0, this is my number 1, and it goes on until I have filled up those last 3 bits. And this is the largest positive number that I could possibly represent, and so it must be, if I were to add 1, I would get 1, 0, 0, 0, and that must be the same as 2 to the 3, which is 8, and if I wanted to then go back to talking about what a sequence of 3 ones represents, then it must represent 7. So this is the number 7, basically. The largest positive number that this system could allow me to represent is the number 7. If I try to go one further, I flip to a negative. Now, this is in fact a weird negative number. Mathematically, we would certainly not allow this, because this would be the number -0, and it would not be identical to +0. Now, in math, this is simply not allowed, right? There is only one number 0. There are lots of very good reasons why there should only be a single negative or 0, and it should neither be negative nor positive. But in any case, the point is that with this system, we would end up having 2 instances of 0, and that ends up causing a whole lot of headache. Besides the very simple fact that you should only really need a single 0. There isn't utility for a second 0. So although this is a simple system, it is wasteful and it causes problems. But if we were to just continue with it, this is the whole idea of one's complement. And it's a good way to just get started with thinking about how you would try to achieve the behavior of simulating negative numbers with 0s and 1s. It's just a start, but we'll get to 2's complement, which is a better idea. But in any case, if we carry the idea along, then the next number is a good number. It's -1, and then the one after that is -2, and so on. And we eventually get down to 1, 1, 1, 1, which would be -7, and that's one's complement. Okay. I've degraded it enough in talking about it to, I think, convince you that we don't want it. But it does make sense. It has a certain kind of simplicity of logic, so that's nice. But let's think about how we would do this if we tried to design it better. Well, if you again think that all zeros is our number 0, and this is 1. Continues until we get to all 1. And I'm thinking now about unsigned integers, right? And so this would be our number, 2 to the 4 16, so this is 15, okay? And then if you add 1, you get an overflow, and it takes you back around to 0. Well, what if we simply set the overflow somewhere else, right? So in a sense, what if what we did was we let this go half of the way? So I guess, maybe let's scratch this out. We know that that's how signed integers worked, but what we're going to do is maybe modify that so that we can go half of the way. It is nice to be able to, use half of your numbers to represent positive or non-negative numbers. So let's go to here, and then say 0, 0, 0, 1, 0, 0, 0. What am I talking about? 1, 0. And then so on until we get to 0, 1, 1, 1. Now, rather than letting the next number be some extra instance of 0, as we've seen up here, that if we added 1 to this, we would get 1, 0, 0, 0, and that in the previously discussed system would get treated like a negative 0, which we don't want. Then what if we allowed this to send right over to the other end of the negative numbers, which are then allowed to progress back towards 0, right? So in a sense, rather than cycling with the unsigned integers going all the way to the end and then with an overflow that cycles back around to 0, instead we get a cycle just like that, but it sends us all the way over to here. And so, in effect, what this would mean is that the very next number would be over here at the far end, the far left end, as 1, 0, 0, 0. We don't maybe just yet know exactly what negative number that would be. We just know that it's to the left of 0. And then the next one would be a less negative number, so to speak. It would be closer to 0. And this would progress until the penultimate number right before 0 would be all 1s. And then that would get us over. Maybe I'll separate these by commas just in case there's any readability issue here. But the point is that this would be our system. And this system is called 2's complement. And as I said before, it is always good to know what a sequence of all zeros means. It is also good to know what a sequence of all 1s means. And in 2's complement, a sequence of all 1s means -1, always. And that's true if we use 4 bits, but it's just as true if we used 8 or any other number. It is, I think, obviously interesting to ask, if you have a given positive number, how do you negate it? How do you get its negative? And if you have a given negative number, how do you negate it and get its positive? Let's just write down a few of the negative numbers that we know quite well, right? We already know that this is -1. If we went 1 to the left, we would get 1, 1, 1, 0. That is 1 to the left, and that would be the number -2. And this is already enough to get started thinking about how do you take the number 1, negate it, and get the number -1. So if you're looking at the number 0, 0, 0, 1, you want to know how to negate this. Now, a decent guess right from the beginning could be that you bit flip every one of these bits, right? What if you took the number 1, 1, 1, 0, bit flip everything? That almost kind of just feels like negation. So maybe that's the negation of the number 1. But if you did have the negation of some number, then what you should get when you add them together is 0. Is that what we get? Well, clearly no, right? When you add these two numbers together, 0, 0, 0, 1, 1, 1, 1, 0, you're guaranteed to get the sequence of all 1s. Now let's just, before we think too much more about that, do it all over again with the number 2 just to make sure that some of these patterns repeat when we pick any number. And I think it's clear, right? If you pick any number, like you pick the number 2, so that's 0, 0, 1, 0. You bit flip, so that's 1, 1, 0, 1. You sum the number with its bit flip, and you get the sequence of all ones. So, and I think you can pretty quickly convince yourself that this will always hold. That if you take a number, bit flip, sum the two numbers, you will get the sequence of all ones. Now, what we actually want is the sequence of all zeros from this. So this is not the negative, right? If you bit flip a number, it is not quite the negative, but dear Lord, you are so close, right? You're just one off, right? A sequence of all ones, as we have established, is the number -1. That's how in 2's complement we represent -1 is with the sequence of all ones. And so when you take a number, bit flip, and add that to your original number, you get -1. So what that seems like, in order to get to 0, is you need to add one more. So that's how you get the negative of any number, is you bit flip and then add 1 to kind of make a correction for this offset that you seem to get, because it lands you at a sequence of all ones, which again is -1. So the negative of, let's just write down a random number, and this time I won't even constrain myself. These ideas will all carry over no matter how many bits you have. So I'm going to write down a random number of bits. I'll say 0, 0, 1, 0, 1, 1, 1. That's my number, and we could interpret this is clearly a positive number. Oh, by the way, it is worth remarking that non-negative numbers in 2's complement still always lead with a 0. But the exact way in which the sequence of negative numbers goes is effectively just in the reverse of what we said for 1's complement. But in any case, I don't want to just sort of like, that's not that interesting for me right now. So I don't want to go too far into talking about that. I just want to tell you that if you want to know whether a number is negative in 2's complement, it still is enough to simply inspect the leading bit. That is still a sign of whether the number is negative or not. A 0 means positive or non-negative, and a 1 means negative. And it means strictly negative, by the way, right? If you've got a leading 1, it cannot be the number 0. It has to be a strictly negative number. But anyway, okay, getting back to the point here. So you could tell that this is a positive number, and if I want the negation of it, then what I should do is first bit flip and then add 1. In this case, adding 1 is really easy because that leading or that rightmost bit is a 0, so all I do is this. And that's how you get the negation of a number in 2's complement, which is, in fact, not that bad. I mean, how would you negate a number in 1's complement? It's so much easier. You simply go to the leftmost bit and flip it only, because that was like the sign bit. All it does is control the sign of the number. So, okay, it was easier to negate in 1's complement, but negating in 2's complement is not that bad. Now that also, right, so having discussed all of these things, I think maybe one last thing that we want to make sure that we understand is what is the least value that can possibly be represented, and also what is the largest value on the positive end that can possibly be represented, in this case, by 4 bits using 2's complement. And I think you can fairly well reason that over here, if you ignore the leading 0, because we know that just makes the number positive, and you just consider the remaining 3 bits, then, by a principle like what we've already talked about in the previous video, with 3 bits, you can represent 2 to the 3 numbers. And so here we can represent 2 to the 3, that's 8. We can represent 8 numbers, and since we're including 0, then this number is 7. We've also seen already, not too long ago, that sequence of 3 ones is the number 7, so you could have reasoned that however you want. But let's just generalize this to say, in 2's complement with n bits, the largest number you can represent is 2 to the n minus 1, right? So 2 to the n minus 1, okay, that's like any power of 2 is just because every single one of these gives you a choice of two things, a 0 or 1, and you get those n minus 1 times. So 2 to the n minus 1 is basically how many numbers you can represent, but because we start by representing the number 0, then if we want the largest number that can be represented, then it is offset by 1, explaining that final minus 1. So that is the largest number that you can possibly represent. Now, let's take this number. And by the way, I've talked about how you can take a positive number and get its negation, and I think I'll let you just think about how it works exactly the same way if you do this to a negative number. So how do you negate a negative number? It's exactly the same process. Bit flip everything, add 1. That always works, whether the number was positive or negative. So if we would like to know what this number is, we bit flip everything, add 1. And by the way, it's a negative number, but what I'm getting here is the negation of it, right? So that was a negative number. I'm getting its positive version, so to speak, which is, right, so then I add 1, and so it becomes this. And so this is, like you do have to represent, or, think about this as if it were an unsigned integer. But as an unsigned integer, 1 followed by all zeros. Now, it turns out that with this system, there's yet another way to think about this. And this, every time you get a new way of thinking about the same thing, it might be helpful and productive. And here it is. So just in the way that we had formulas that took a number, let's just do this exercise again. So let's say 3, 4, 5 is in just decimal, right? Just standard mathematical decimal numbers, just to repeat this logic. That is 3 times 10 to the 2 plus 4 times 10 to the 1 plus 5 times 10 to the 0. There is a similar, but of course slightly different formula for representing numbers in 2's complement. And that idea is that if I write down, like let's just say here, let's take this number and I'm going to come down here and apply the formula, then what you can do is you can in fact regard this as all of these bits being positive in base 2, and this bit always necessarily having a negative sign, but sometimes that negative sign is 1 and sometimes the negative sign is 0. As a formula, then this would be, let's go from right to left. So if I start at the right, then I'm going to say that that's 1 times 2 to the 0 plus, then 1 times 2 to the 1 plus, 0 times 2 to the 2 plus, but actually minus. This is the idea. When we get to the leftmost bit, which we now are at, so when you reach the final left bit, it's no longer a plus, it's a minus. That's how you get this formula for 2's complement, which is that becomes minus 1 times 2 to the 3. And then you can see how they are sort of simplifying that up here, that it's the same thing, right? This thing right here is -8, so that's -8 plus, and then are they yet writing it? Yeah, so I think we're writing it in reverse order. So this will be 0, this will be +2, and then this will be +1. But anyway, so the point is that there is this nice formula in terms of base 2 expression that allows you to interpret a 2's complement number. And, so that's maybe just a curiosity, but then it has this interesting, useful feature that if you had a number with a fixed number of bits, and sometimes, it happens that you would like to give it more bits, right? Like, if you think about how, if you took, say, the number 1011 as we have it now, but let's say that you want to give it more bits, and your instinct is maybe, like, let's say that we want to give it 1 more bit, then you write a 0 over here. Well, that is unfortunate because it used to be a negative number because the leftmost bit was a 1. Now it's a positive number. You've clearly changed the number. Turns out that if you actually extend it by 1, then what you have effectively done is you flipped this positive and created a new number twice as big, right? Because it's got an extra power of 2, and made that negative. So effectively, by doing this, by giving it a 1 rather than a 0, then what you're doing, I guess maybe we can just point up here since the numbers are already written out, but you're taking this 8, which used to be negative because it was written to the leftmost position here, you're flipping it positive, but then you're creating a new digit of negative 16 because you wrote a negative 1 here. What does this do as a net effect? It does net nothing, because what did you used to have? You used to have negative 8. What do you have now? You have 8 plus negative 16, which is again negative 8. So these are the same, right? So by prepending an extra bit of 1, you don't change the value of the number, which is very nice. And this pattern continues. Let's do it one more time. What if I flip the 16 positive, so it becomes 16 plus 8 plus 0 plus 2 plus 1. So because I'm going to prepend, right? Like what this is supposed to correspond to is what if I prepended another 1's digit to the left. So this would be 0b, 1, 1, 1, 0, 1, 1. So that's what I'm going to represent. But I guess I need to give myself a little space because I'm not only going to take that 16 and now turn it positive because that 1 is no longer the leftmost bit, so it's no longer negative, it's now positive. But now I have an extra bit further to the left, so that's going to correspond to a 32, right? Twice as big, but negative. And what I've done is I have replaced now negative 16 with negative 32 plus 16, which is still negative 16. So these are the same thing. So anyway, the point is, right, the big upshot of this idea is that if you are ever in a situation where you have a 2's complement number and you would like to pad it out with extra bits. Oh, but and I guess, and by the way, this is for a negative number. And if you had a positive number, let's say that you had, 101, I'll write 0b, 101. So that's, sorry. And then I would need to lead it with a 0. So 0b like that. So this is a positive number. What positive number is it? Let's just check. That's 2 to the 4, so that's 4. And then 2 to the 0, so that's 1. So 4 plus 1 is 5. So this is the number 5. And then what if I want to pad this out with extra bits? Well, then I want to extend by zeros because I don't want to add anything. And I want to keep that leftmost bit 0 because this number is supposed to be a positive number. So now I pad it out with zeros. So the logic is this. If you have a positive or at least non-negative number, and you would like to have exactly the same number but represented in 2's complement with more bits, then whatever was your leftmost bit is exactly the thing that you want to extend out to the left, right? Make copies of that out to the left until you have the number of bits that you desire. If it was positive, that means making leftward copies of 0. And if it were 1, then that means making leftward copies of extra bits of 1. And in 2's complement, that will keep the number the same, but give it extra bits. It may be worth just remarking that if you were dealing with unsigned integers, by the way, remember, right, so we've got unsigned integers. Were those bad? No, those were not bad. It's just that they couldn't represent negatives, which maybe we want to. But there was no flaw in the system of representing unsigned integers. When we went to 1's complement, it made a certain kind of simple sense, but it was flawed. So we kind of eliminate 1's complement. But then we replace it with 2's complement. So anyway, but if we go back to unsigned integers where we still like that system, now we want to ask maybe, how do you pad that out with extra bits? And there the story is very simple, right? Just you always pad out with leftward zeros no matter what the number is, because that just adds nothing to an unsigned integer. Okay.